Okay, welcome to the Unit 2 revision session on sequences and surds. So first off, here's an example of a sequence, 3, 5, 7, 9, 11. As we can see, it follows a simple rule where we add 2 each time. Now, this is what we call our first term. Here's our second term, our third term, and so on. What we can do, instead of having just a sequence like this, we can have a general rule for our sequence which allows us to generate any term in that sequence. We call that general rule the nth term. So for example here, the nth term of this particular sequence is 3n plus 4. Now in order to work out what the first term is, we need to let n equal 1. To work out the second term, we let n equal 2. The third term, n is 3, fourth term, n is 4, and so on. If I also wanted to work out the 100th term, what would n be? Well, n would be 100 to work out the 100th term. So now, to work out what the first term is, we just plug n equals 1 into this formula. So when n is 1, 3n must be 3, add 4 is 7. When n is 2, 3 times n is 6, add 4 is 10. When n is 3, 3n is 9, add 4 is 13. When n is 4, 3n is 12, add 4 is 16. Now if we're doing this right, we should have a difference that is the same each time. So 7 add 3 is 10, 10 add 3 is 13, 13 add 3 is 16. So it seems like we're doing it right, and without doing any more calculations, we can work out that this one must be 19. Then to work out the 100th term, 3 times 100 is 300, add 4, 304. So let's have a look at another sequence then. This time, our sequence is given by 2 times n squared. So again, we're going to start off with n being 1. This time, remember, we need to square it first before we multiply it by 2. So 1 squared is 1, times 2 is 2. 2 squared is 4, times 2, 8. 3 squared is 9, times 2, 18. 4 squared is 16, times 2 is 32. 5 squared 25, times 2 is 50. This time, because we've got an n squared rather than just an n, we don't have the same difference each time. But that's okay, it's just because it's a different kind of sequence. Finally, to get the 100th term, well, if n is 100, n squared is going to be 10,000 times by 2 is going to be 20,000. So we've looked at generating a sequence from its nth term. Now let's look at going in reverse. So let's take this sequence, 2, 4, 6, 8, 10. This is obviously the 2 times table, and it goes up in 2 each time. Now this sequence here can be generated by the nth term 2n, because this says any number multiplied by 2. So if we start with n equals 1, 2n is 2, n is 2, 2n is 4, n is 3, 2n is 6, and so on. So similarly this, the 3 times table, goes up in 3s each time, and this is given by the nth term 3n. So let's look at a slightly harder kind of sequence. Here we have 5, 8, 11, 4, 14. This sequence goes up in 3s each time. This means it's a little bit like the 3 times table. So it's going to start off the nth term the same as up here, with 3n. But we know this isn't the 3 times table. This is a 3 times table in disguise, so to speak. The actual 3 times table goes 3, 6, 9, 12. So how do we get from the 3 times table to our sequence? Well, each time we need to add 2. This means that nth term is not just 3n, this can be 3n plus 2. Let's have a look at another example of this. Here's my sequence, 1, 6, 11, 16. So this time, it's going up in 5s each time. So it's a bit like the 5 times table, in which case my nth term is going to start with 5n. But the 5 times table actually starts 5, 10, 15, so on. So how do I get from the 5 times table to my sequence? Well, I just have to take away 4 each time. But our sequences might not always go up. Here we've got another sequence, and this time it goes down in 3s. So our nth term is going to start with minus 3n this time. But it's not the minus 3 times table, because the minus 3 times table is minus 3, minus 6, minus 9. So how do I get from minus 3 to 23? Well, I have to add 26. So my nth term is minus 3n plus 26. Okay, so next let's look at generating sequences from patterns. So here I have a series of diagrams, and I'm first asked to draw the next diagram in the sequence. Well, I can see that I've got 1 square, then 3, then 5, so my next diagram is just simply going to have 7 squares in it. So here are 7 very badly drawn squares in my next pattern. So how many squares are there in the nth diagram? In order to work this out, I need to know how many squares there are in each pattern. So I've got 1, 3, 5, 7. So I've got a pattern of numbers now, 1, 3, 5, 7. Now, this pattern is going up in 2s, so I know my nth term is going to start 2n. And to get from the 2 times table to this sequence, I need to take away 1. Now that I have this nth term, I can work out how many squares there are in the hundredths diagram. So in the hundredths diagram, n is 100, so 2 times 100 is 200, take away 1 is 199. So that's all we need to know for sequences. Let's look at our other topic, surds. So numbers like the square root of 2 and the square root of 5 are called surds. These are numbers which cannot be written exactly as a decimal, but go on forever without ever repeating. Now we have some very important rules for surds. These are as following: that if we multiply two surds, their answer is just the square root of the two numbers multiplied together. So for example, the square root of 2 times by the square root of 3, that's just going to be the square root of 2 times 3, or the square root of 6. Similarly, if we divide two surds, the answer is just the square root of the numbers divided. So for example, the square root of 20 divided by the square root of 2 is just the square root of 10. But finally, we can't just add two square root of 2 numbers together. So for example, square root of 2 plus the square root of 3 is not the square root of 5. We're not allowed to just add those two together. What we can do though is we can simplify surds. Let's take the square root of 20. Now the first thing I'm going to do is I'm going to find out all the factors of 20. So 20 can be written as 1 and 20, 2 and 10, or 4 and 5. Now what I want to pick is a pair of those where one of the numbers is a square number. So I'm going to pick this one here because 4 is a square number. So the square root of 20, that can be written as the square root of 4 times by the square root of 5. So I've split up 20 into 4 times 5, so the square root of 20 is square root of 4 times square root of 5. But I can work out what the square root of 4 is. The square root of 4 is 2, and I've still got the square root of 5. And just because I'm feeling lazy, I'll write that without the multiplication sign, 2 root 5. Okay, so let's look at a different kind of question. Here I'm asked to simplify 5 square root 7 times 2 square root 3. So let's write down what this means first of all. So I've got 5 times by the square root of 7, because that's what it's written as from not being lazy, times by 2 times the square root of 3. Now when I'm multiplying, I can change the order things are in. So let's change this around. So I've got 5 times 2 and the square root of 7 times the square root of 3. So I'm dealing with the whole numbers and the surds separately. Now 5 times 2 I know is 10, and the square root of 7 times the square root of 3 is just the square root of 21. So this I can write as 10 square root 21. For our final example, let's look at a similar question. 3 root 3 times 2 root 6. Well, I know I can just multiply the two whole numbers together to get 6, and I can multiply everything under the square root signs. So 3 times 6 is 18. So I've skipped out a few steps there to get to this answer. But can I simplify this surd? Well, let's have a look. 18, that's 1 times 18, or 2 times 9, or 3 times 6. Are any of those there square numbers? Well, yes. This pair here has a square number in it. So I can write this as 6 times by the square root of 18, which is the same as 6 times by the square root of 9 times by the square root of 2. Now the square root of 9 I can work out is 3, and 6 times 3 is 18 times by square root of 2, which finally simplifying gives me 18 square root 2. So that's everything that we're going to do on sequences and surds. Thank you very much for listening.